Let us now take a look at the symbols of the elements in the periodic table. If you have only one letter in the symbol, it will be a capital letter. For example, capital H is for hydrogen, capital B is for boron, and so on. If, however, you have two letters in the name of the element, the first letter will be an uppercase letter. For example, take a look at beryllium. The first letter is capital B. The second letter is lowercase b. That is how we write the symbols of elements. Take a look at calcium. The first letter is uppercase C. The second letter is lowercase a. If you write calcium like this, that is not calcium. That would be California. The next thing we want to learn about are the numbers you see below the elements. These numbers below the symbols of the elements, these numbers are called atomic masses. And the question is, what are they? To understand what they are, we first need to learn about isotopes. So, what are isotopes? The very first thing to remember is that the identity of an element is solely determined by how many protons you have in the nucleus of the element. Which means that you can have different numbers of neutrons and different numbers of electrons, but the number of protons must be unchanged because it determines the identity. If you have atoms of the same element that have the same number of protons, but different numbers of neutrons, those atoms are referred to as isotopes. For example, take a look at these two isotopes, chlorine 35 and chlorine 37. The number of protons in each of them is 17. The number of electrons in each of them is also 17 since they are neutral. And the number of neutrons in the first one, which is called chlorine 35, is 18, while the number of neutrons in the second one, which is called chlorine 37, is 20. And these two are called isotopes because although they have the same number of protons, but the number of neutrons in their nuclei are different. We can also define isotopes as, isotopes are atoms of the same element with the same atomic number but different mass numbers. Because if you take a look at it, these two isotopes, they have the same atomic number, the same number of protons, but they have different mass numbers. And the different mass numbers is why they have different numbers of neutrons in them. Let us take a look at this question, just to be sure that we understand the concept of isotopes. Consider the following pairs of atoms, in which X represents the chemical symbol of the element. Which of the pairs are isotopes of the same element? To be isotopes of the same element, they must have the same number of protons. So, in that regard, these two have the same number of protons. This is disqualified because they have different numbers of protons. So, will this be disqualified because you have different numbers of protons? But they are isotopes because they have different mass numbers. Let us now answer the first question I posed. How do we determine atomic masses? To answer that question, let us go back to the two isotopes that I used as an example earlier. Chlorine 35 and chlorine 37. In nature, chlorine 35 is more commonly found than chlorine 37. Actually, about 75% of all the chlorine atoms in nature are chlorine 35, while the remaining about 25% of all chlorine atoms in nature are chlorine 37. These percentages are called natural abundances. This is now the question. Which mass should we use to represent all chlorine atoms? We cannot use 35, although it is a mass number of chlorine, because chlorine 37 also exists. And we cannot simply use 37 because chlorine 35 also exists. The number we use to represent all the chlorine atoms in nature is found by what is called weighted averaging. And how do we calculate the weighted average for chlorine? This is how we do it. We multiply the natural abundance by the mass number of each isotope. This is what I mean. For chlorine 35, we multiply its abundance, which is 75%, by its mass number. We add that to 25% multiplied by the mass number of chlorine 37. If you multiply 75 by 35 and you divide by 100, you should get 26.25. And if you multiply 25 by 37 and divide by 100, you should get 9.25. And if you add these two together, you should get 35.50. And the unit for atomic mass is AMU. If you look at the periodic table and you look for chlorine, you will see that the number under chlorine is approximately 35.5 if you round to one decimal place. So all of the atomic masses that you see at the bottom of each element, as I'm indicating, all of them are found using weighted averaging. Let us take a look at another example. In this question, we want to calculate the atomic mass of magnesium using the information provided in the table. We have three isotopes: magnesium 24, which actually has a mass number of 23.99 AMU. This AMU means atomic mass unit. Magnesium 25, which actually has a mass number of 24.99 AMU, and magnesium 26, which actually has a mass number of 25.98 AMU. The corresponding natural abundances for each of the isotopes is also given. Let us now calculate the atomic mass for magnesium. That would simply be 78.99% multiplied by 23.99. Again, remember, we simply multiply the natural abundance by the mass number plus 10.00% multiplied by 24.99 plus 11.01% multiplied by 25.98. If you multiply out the numbers and you add all of them together, you should get 24.309099 AMU, which, if rounded to 2 decimal places as given in the mass numbers, that would be 24.31. And if you take a look at the periodic table and you look for magnesium, you will see that magnesium actually has an atomic number of 24.31 approximately. That is how all of the atomic masses are calculated. Let us take a look at one more question. There are three naturally occurring isotopes of potassium: potassium 39, potassium 40, and potassium 41. If the atomic mass for potassium on the periodic table is given as 39.10 atomic mass unit, which isotope of potassium is most abundant? For this type of question, you actually do not need to do any calculation. Let me explain why. Let us take a look at the question we just completed. If you observe, you will see that the atomic mass that we got will be closest to the mass number that has the biggest natural abundance. Let me repeat. The atomic mass that we got will be closest to the isotope with the largest natural abundance. So, if we come back to this question that is asking us which isotope is the most abundant, that would be the one that has its mass number closest to the atomic mass, and that would be Potassium 39. It is the one that is the closest to the atomic mass in the periodic table, and it makes sense. Don't forget, we are using weighted averaging. The isotope with the largest mass number will have the largest weight in the average. So the answer to this is potassium 39.